Hello friends, welcome to this video which is second part of the Symmetric group SN, and if you haven't seen the first part, please go and check now. In this video I will talk about conjugacy classes of the Symmetric group SN, and we'll see how can we count the number of elements in a given conjugacy class. So let's start. Let G be a group. G and H are two elements in G. We say that G and H are conjugate to each other if there exists another element X in G such that XG X inverse is equal to H. Okay, and so we'll use the notation G tilde H if G is conjugate to H. So let's see some of the properties which conjugacy satisfies. So you can see that G is always conjugate to itself. You can use the identity element. So identity inverse of identity is identity itself, and so EGA is equal to G. So G is conjugate to itself, which is the reflexivity property. Conjugacy is also symmetric, that if G is conjugate to H, then H will be conjugate to G, and you can see that easily. If you have a X such that XG X inverse equal to H, then you can take the element X inverse and then X inverse H times X inverse inverse, which is again X, will be equal to G. Then the third property is that conjugacy is also transitive, that is if G is conjugate to H and H is conjugate to K, then G is conjugate to K. And again, it's not very hard to see. If G is conjugate to H, it means there is a X such that XG X inverse equal to H. H is conjugate to K, so there is a Y such that YH Y inverse is K, and then you can use the element YX, and you can see that YXG YX inverse, which is X inverse Y inverse, will be equal to K. So you know that once these three properties are there in a relation, this relation is called an equivalence relation. So conjugacy is basically an equivalence relation on the group G. So it's a general property of equivalence relations that whenever there is an equivalence relation on a set X, it partitions the set X in disjoint classes. Okay, so conjugacy relation on the group G will also partition G into classes, and we call these classes conjugacy classes. Okay, so now given a element G in the group, what is the meaning of conjugacy class of G? These are all elements of the type XG X inverse where X in G. So basically you take the element G, and if you want to find its conjugacy class, you keep finding its conjugates in the form XG X inverse for all element X in G, and in this way you will get the conjugacy class of G. But in this video we'll focus on the symmetric group Sn, and we want to know that what are the conjugacy classes, how many are there, and then in each conjugacy class how the elements look like, and how can we find the sizes of different conjugacy classes. So let's discuss the first thing. The number of conjugacy classes of symmetric group Sn is equal to the P of n, which is basically the number of partitions of n. So for example, if you are looking at S5, then number of conjugacy classes will be 7, because partition number of 5 is 7. What is partition number? So you can partition 5 in positive integers in 7 ways. So for example, 5 can be written as 5, or 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1, and then adding 1 5 times. So these are 7 ways to partition 5 into positive integers, and hence P of 5 equal to 7, and hence S5 has 7 conjugacy classes. So this way you can find partition of any n, and you can find number of conjugacy classes in Sn. So next we'll discuss in a given conjugacy class of Sn how elements will look like. Okay, so now we know that partition of n is in one-to-one correspondence with conjugacy classes. So given a partition of n, you can associate a conjugacy class, and each conjugacy class is uniquely associated with one partition. So suppose you have a conjugacy class, so you have a unique partition associated with it. Then how can we, using that partition, how can we find that how will elements in that conjugacy class look like? So for example, take the example of S5, and consider the partition 2 plus 2 plus 1. Okay. Now corresponding to this partition, there is a conjugacy class of S5. Okay. So what are all elements in this conjugacy class? In this conjugacy class, all elements will have cycle type 2 to 1. What does that mean? That there will be two cycles, okay, and there will be one cycle. So one cycles are we don't write when we write the disjoint cycle composition of any permutation. So basically there will be two cycles. So now all two cycles will be in this conjugacy class, the conjugacy class associated with the partition 2 plus 2 plus 1. So I have written all two cycles, and they will be in this conjugacy class. There are a total 15 such elements in this conjugacy class. So an important question is that given the cycle type, for example, in this case it is 2 to 1, how can we find all elements of S5 which has this cycle type? For example, how can we count all these elements? So in this case I have written that the number is 15, but how can we come up with given any cycle type? So next we will discuss that. So suppose you are looking at a conjugacy class of Sn, and now we know that this conjugacy class can be uniquely associated with a partition of n, and suppose this particular partition has n1 ones, n2 number of 2's, and nk number of k's. Of course k is less than or equal to n. So basically we are writing n as 1 plus 1 plus 1. So there are n1 number ones, then plus 2 plus 2, there are n2 number of 2, and then there are 3's, and there may not be. So this n1 n2 can be 0, and there are k's, and we are adding k's, and these has nk numbers. Okay. So for example, suppose take example of 5 equal to 2 plus 2 plus 1. So in this case 1 is appearing only one time, so n1 is 1, and 2 is appearing 2 times, so n2 is 2, and all other numbers, if you'll ask, n3 is 0, n4 is 0, etc. So we don't have to worry about that. We know that n1 is 1 and n2 is 2. So you take these non-zero numbers, then the number of elements in this conjugacy class associated to this partition will be this number. You take n factorial and you divide by 1 is appearing n1 number of times, so 1 to the power n1 times n1 factorial. 2 is appearing n2 number of times, so 2 to the power n2 into n2 factorial. Similarly, you take all the numbers who are appearing, and the last one is k, which is appearing nk number of times, so k to the power nk into nk factorial. Again, let's take the same example. So 5 equal to 2 plus 1, n1 is 1 and n2 is 2, so 5 factorial divided by 1 to the power n1 is 1, so 1 to the power 1, and n1 factorial is 1 factorial. 2 to the power 2, because n2 is 2, into 2 factorial. So 5 factorial, this number is basically 8. So 5 factorial divided by 8 is basically, you can see that. So this is 5 into 4 into 3 into 2 into 1 divided by 8. So this is 50. So let's try to solve some problems based on what we discussed just now. So this problem asks how many elements in a set are conjugate to this permutation in a set. Okay, so first let's write this permutation in product of disjoint cycles. So I start with 1 goes to 4 goes to 7, and 7 goes to 1, so this cycle completes. 2 is not appearing here, so I start with 2 goes to 5 goes to 8, and 8 goes to 2, so this is complete. Now 3 hasn't appeared, which is 3 is going to itself, so this is 3, and then 6 is left, so 6 is going to itself 6. So I delete the 1 cycles because we don't write them in disjoint cycle decomposition. So then what is the cycle type of this permutation? That is, which partition of 8 it is associated to. So you can see that it is associated to the partition 3 plus 1 because there are 2 3 cycles and there are 2 1 cycles. Okay, so then all elements of this cycle type, that is 3 3 1 1, will be in the conjugacy class of this element. Okay, so we need to count all elements of this type. So we just saw, so here you can see that n1 is 2 because n1 1 is appearing 2 times, and n3 is 2 because again 3 is appearing 2 times. So then the number of such elements in S8 would be 8 factorial divided by n1 is appearing 2 times, so 1 to the power n1 times n1 factorial, and 3 is appearing 2 times, so 3 to the power n3, which is 2, into n3 factorial, that is 2 factorial. So what this number is 8 factorial divided by, so this is basically 9 into 4, right? So we write this number, this will be equal to 8 into 7 into 6 into 5 into 4 into 3 into 2 divided by 9 into 4. 4 cancels with 4, 3 cancels with 3, and this becomes 2. So then we see that it is equal to 8 times 7 is 56, and this is 10 times 2, 20. So this will be 0, 2, 6, 12, 2, 1, 1, 1, 2, 0. So this is the number of elements in S8 which are conjugate to this given element. So let's discuss another similar problem so that we can get hold of this concept. So this element of S7 is given, and we have to find the number of elements in the conjugacy class of this element. So you can see that it is kind of the similar cycle type, but now we are in S7. So this is the partition we are looking at is 3 plus 3 plus 1. Here 7 is fixed, you can see. So it's the cycle type 3 plus 3 plus 1. So if you want to count, again n1 is 1 and n3 is 2. So then it will be 7 factorial divided by 1 to the power n1 into 1 factorial, and 3 to the power n3 into n3, which is 2 factorial. So this will be 7 factorial divided by 9 into 2, and this will be 7 into 6 into 5 into 4 into 3 into 2 into 1 divided by 9 into 2. So 2 cancels out, 3 cancels with 3, and this is 2. So this will be 28 times 10, which is 280. So there are 280 elements in S7 which are conjugate to this given element 1, 2, 3, and 4, 5, 6. Okay, so let's look at this different problem which asks how many elements of order 6 are there in S7. So we can solve this kind of problem as well using this conjugacy class concept. So from part 1 or otherwise, you know that order of an element in Sn is basically LCM of lengths of disjoint cycles which appear in the element, in the permutation. So basically, if you partition 7, okay, in different parts, so the LCM of parts should be equal to 6. Then all elements of that cycle type will have order 6. For example, 7 has some partition, 7 has a partition 7, 6 plus 1, 5 plus 2, etc. There are 15 such partitions, but 7 will have order 7. All elements corresponding to this partition will have order 7. This LCM of 6 and 1 is 6, so these will have order 6. LCM of 5 and 2 is 10, so these elements will have order 10. Now since we are counting elements of order 6, we should look at partitions in which LCM will be 6. So in these partitions should contain 3, 2, 1 or 6. So one such partition is 6 plus 1. Another, now we can't get anything else involving 6. So now we should move to 3 and 2. So with 3 and 2 you can get 3 plus 2 plus 2, right? So this is another partition. Another you can get 3 plus 2 plus 1 plus 1. Again the LCM will be 6, and I don't think we can get more. So in these three cases, for these partitions, elements of these elements will have order 6. Okay, so what we have to do is calculate number of elements of this cycle type, this cycle type, this cycle type, and add. So here you can get that elements will be 7 factorial. There is 1 so 1 to the power 1 into 1 factorial. There is a 6, so 6 to the power 1 into 1 factorial. So basically 7 factorial divided by 6, so that would be 7 into 5 into 4 to 3 into 2. So that would be 28 into 30, and that would be 0, 4, 840. Okay, now 3 to 2, this cycle type would be 7 factorial. There are two 2's, so 2 square into 2 factorial, and there is 1 3, so 3 to the power 1 into 1 factorial. So this is equal to 7 factorial divided by 4 into 2 into 3. So this will be equal to 7 into 6 into 5, and then 4 to 3 will cancel out. So this is basically 42 into 5, that would be 5 to the 10, 0, 1, and this is 210. And this will be equal to 7 factorial divided by, there are two 1's, so 1 square into 2 factorial. There is 1 2, so 2 to the power 1 into 1 factorial. There is 1 3, so 3 to the power 1 into 1 factorial. And so basically we are looking at 7 factorial divided by 2 into 2 into 3. Okay, so this will be equal to 7 into 6 into 5 into 4. 3 2 will cancel, there is a 2, so this will be 2. So this is 42 into 10, so 420. So these are number of elements of these cycle types, and since we want all elements of order 6, we need to add 840, all these 3 plus 210 plus 420, and that would be equal to 0, 415 and 2 7, and then 8 to 10 plus 4 14. So there are 1470 number of elements of order 6 in S7. So this is the end of the video. For more such videos, keep visiting us, and thank you for listening.